questions, and the speaker will be Charles Moumont, please.
Yeah, perfect, thanks. Okay, so thank you for the introduction. So I will continue this session about side channel with a quick reminder about it, but we have already covered some subject already. So it's not this one, it's not this one. Okay. Okay. Okay, perfect. So my presentation will be split in 4 parts. So first one is quick background to remind a bit the side channel stuff that I want to speak about. Then 2 parts that will speak about our contribution in this paper. First one, a mathematical part covered by the second part. And the third part will speak about our experimental results. And I will quickly finish with a small conclusion afterwards. So first one, as a background, let's consider a simple case of block cipher utilization that is using a single long-term key for several execution. And these executions are taking several plain text as input, so the input PI. And this block cipher execution is computing the ciphertext CI. And in this simple settings, these block cipher execution are secure in the black box settings. But as long as we consider leakage, an adversary is in fact able to recover small pieces of information about this long-term value, this long-term key value. Each time, in fact, the block cipher is using another input with the same key. And by recombining, in fact, several small pieces of information, is able to recover the long-term key value. And as we have already covered in the first session, a popular countermeasure against such attacks is the masking countermeasure. And considering that the block cipher is masked, basically, we have a situation where it's hard from an adversary point of view to be able to recover the value of the key using several execution. So from these settings, basically, it looks like one of the issues is that we are reusing all time the same value for the key. And that's why another approach is, in fact, based on the fact that we will generate a new fresh key for small batches of execution of the block cipher. So we will generate a new fresh key for several but few executions. And in fact, this is covered by the rocking countermeasure, and it's implemented using 2 primitives. A first one, which is the so-called rocking function that is using the long-term key k, and that is generating a new fresh key, star, for few execution of the block cipher. And the block cipher in that case is not protected. And in that settings, if an adversary wants to recover the key used in the block cipher execution, he has to do it. He has to be able to do it using only few leakage that he is obtaining from several execution, but few execution. And in practice, this settings is quite hard this kind of attack is quite hard to achieve when we are considering hardware implementation. But looking at that, it may be a bit weird to choose to use rekeying instead of directly protecting the primitive that you want to protect, because we have 2 primitives, so we may have additional costs. And in fact, it turns out that due to their, by nature, in fact, block cipher are nonlinear, and it turns out that implementing nonlinear operation in a masked manner is something quite costly and has, in fact, a quadratic cost with the security parameter, so the masking order. And for high level, on the contrary, for high level masking, high order masking, sorry, so a lot of shares used, it turns out that rocking, mask rocking implementation turns out to be to have a linear cost instead of a quadratic one, and especially if this rocking function has some key homomorphic property. So that's the main interest of using, in fact, rocking instead of directly protecting the primitive that you want to use. Focusing a bit more on the hacking function. So we have spoken about a first attack path from an adversary point of view, which is attacking the hacking function based on the side channel directly. But if we consider that this hacking function is masked, then we can consider that this attack path is quite difficult to achieve in practice. But there is another one, which is what can we recover from the long-term key value based on the information that we obtain from the fresh key. And there is already several works in the literature that are trying to analyze such situation and that are trying to introduce hacking function. And they differ by their adversarial model. And a first work that has been published, consider that the adversary obtains noisy leakage of the fresh key. And in these settings, they propose to use a final field multiplication as a hacking function, which is defined on the slide, and which has the advantage of being key homomorphic, so easy to implement in a masked manner. So we have efficient implementation for that, but a drawback of this hacking function and this adversarial model is that it turns out that we require a significant noise level is required to have security. A second one, it's in fact the total opposite on the spectrum of adversary. Consider that we have unbounded leakage. So basically that means that the adversary has access directly to the value of the fresh key star. And using this adversarial model, they propose to in fact build a hacking function using a weak PRF, which is basically based on rounded inner product as defined on the slide, and that has also some key homomorphism properties, so may be quite easily implemented in a masked manner. But the drawback for this proposal is that the key size has to be quite big, and that has some costs and some impacts on the performance of the implementation. A third one that, in fact, will be the basics for our contribution is considering that the adversary is obtaining noise-free leakage of the fresh key K star. And I will focus a bit more on this one. So basically, the proposition for the hacking function is based on a final field, prime field matrix product as defined there on the slide, and which is also homomorphic, so has the advantage of being easy to mask. And we can see, and it was in fact done in the paper, we can, in fact, the first observation is that it's quite similar to the weak PRF proposal that was done in crypto dark matter. So as a reminder, this weak PRF was based on two steps, let's say, it was built on two steps. A first one, which is a matrix product, and the second step, which was a nonlinear mapping operation that was applied on top of the result of the product. And in fact, in this paper of 2021, they consider that the nonlinear mapping operation is performed by the physics of the circuitry instead of having a dedicated circuitry that is performing the computation. So in fact, that turns out to be quite interesting, speaking about implementation, because there is in fact no cost for this nonlinear mapping operation since it's done by the physics directly. But on the other side, the leakage is free in terms of implementation. The leakage function, the nonlinear mapping, so in that case, is free, but it's not controlled either by the adversary or by the designer of the countermeasure. And digging a bit more into the proposal of hacking function, so they also introduce a new hard learning problem. Hard physical learning problems is in fact, we are using the physics in that case, which has some similarity with the learning with error and learning with rounding problem. And which is defined as this. So basically, in these settings and using this assumption, it's hard, in fact, to from an adversary point of view, to recover the value of a long-term key K if he's accessing the value of the R value, so the initial vector that is in fact a public value, and leakage, noise-free leakage of the fresh key K star. And to analyze it more formally, this of course requires an assumption of the physical leakage function. And in the CHES 2021 paper, they consider only Hamming weight as a leakage function. And in fact, our work, so in our paper, we try to generalize the security of such a construction for a broader class of leakage function. So yeah, what do I mean by generalization of the leakage function? So as I told you in CHES, they were considering Hamming weight only, and it turns out that a more realistic model is in fact to consider that the leakage of an internal value inside of a circuitry can be expressed as a weighted sum of some coefficient alpha and some basis function of this internal value, but let's consider that this basis function is in fact giving the bit of the internal value at the index I. And it turns out that this is more realistic because it covers cases where, for example, in the circuitry, we have different capacitive loads and different bits inside the circuitry may leak differently. And it also covers the first case that was analyzed, so the Hamming weight. Let's consider that all the coefficient alpha I are equal to 1. We have the leakage function that is in fact equal to the Hamming weight. When trying to analyze more formally the security, a first observation that we have made is that if the leakage function, the physical leakage function, can be interpreted as a function over the prime field that is used in the computation of the Röcking function, so the prime field FP, then an adversary, a natural path of attack, but yet heuristic, but natural one from an adversary point of view, is to build an algebraic system over FP using measure that he is acquiring and solve it in order to recover the value of the long-term key. In order to analyze a bit more in details, we introduced the class of leakage function that we denoted as S-bounded pseudo-linear leakage function, and which is detailed here, and which is in fact quite similar to the one that I have just explained, and which is also in fact a weighted sum with some assumption and some hypothesis, like regarding the analysis, this analysis using this S-bounded pseudo-linear leakage function will in fact hold as long as the hypothesis that we are making on the physical leakage holds too. And these hypotheses are the following. So we consider that the physical leakage has a bounded degree, and that we also consider that the coefficients are bounded. And for all our practical cases that we have analyzed in our paper, it turns out that leads, if we are considering the simple attack path that I've just explained, that leads to an attack complexity that is bigger than our security parameter. To give a bit of intuition, so let's consider a simple case of S-bounded pseudo-linear function using 3 coefficients. So I've written on the slide the representation of this function FA. So the coefficients are 1, 2, and 2. And on your left, you have a table that is in fact defining all the value of the S-bounded pseudo-linear function. And you can see that we have a function that is linear over the bits, but when we consider the polynomial representation of the function over FP, it turns out that this leads us to a nonlinear function, as shown, for example, with the degree 6 monomial term. And the simple idea behind that is that even if we have a function that is linear over the bit, that leads us to solving algebraic system with highly nonlinear function, which turns out to be complicated. I will detail a bit more afterwards. Maybe just some additional details that will help the understanding of the next slide. For this S-bounded pseudolinear function, we define the main image as the image of the function that has the most pre-image. And the main image, the main pre-image size as the amount, in fact, of pre-image for this main image. And in our case, we have two main images. We have 2 and 3, and their pre-image size is equal to 2. And we denote the pre-image size as VFA. So considering a concrete attack path, here I put on the figure in fact the system that we are dealing with, considering the LWPR recurring function. And on your left, you have the long-term key matrix, which is made of m rows and n+1 columns. You have the public value R, and then you have the fresh key that is computed out of the multiplication on your right. And in fact, if we consider a serial implementation of this multiplication, the fresh key is in fact computed wordwise. So we will be able to measure the leakage of a single word of the fresh key K star, as depicted in orange on the slide. And an adversary in that situation, knowing the value FA and obtaining the value of the leakage L, and knowing also the value of the public value R, is able to solve the algebraic system in order to recover the first row of the matrices of the long-term key. And in order to do that, he has so solving this system has a complexity that is depicted there. So it is equal to the amount of monomials of degree at most equals to d to the square, and d is in fact the degree of the function fa, which we prove to be lower bounded by the pre-image size. And you can see for more details in the paper, but we have also a lower bound on the value of the pre-image size, which turns out to be quite big. And putting the value of the degree on the complexity turns out to be something quite big too. That's a single analysis path that we have made, but there is all other contribution on the mathematical part in the paper. For example, we have considered also an adversary that tries to solve a noisy linear system, and it turns out that this is mainly based, so the security is mainly based on the nonlinearity of the function fa. We have also, from this serial implementation, make the analysis for a parallel implementation, which is in fact required in a practical case to have good security. And also we have made an analysis for worst case S-bounded leakage. So for example, worst case S-bounded leakage is the case where an adversary is able to recover a leakage value that has in fact small amount of pre-image, so which turns out to be quite easy to solve. So now that I've explained quickly what we have done from the mathematical point of view in our paper, there is another stuff that we have to focus on in the paper, and we are in fact doing it, is to assess the validity of our assumption on the physical leakage function. And a first one was, so we have our experimental setup first. We consider the same architecture as the chess paper, an hardware implementation and parallel one. So that means that all the words of the fresh key are generated in one single cycle. And so the parameter instance are using 4 rows and 5 columns for the long-term key matrix. And we also consider 3 congestion level for the hardware implementation in order to highlight the fact that using such a general leakage model makes sense. So we, in fact, implemented the same architecture on an FPGA using an unconstrained implementation, a constrained one, and a virtually amplified one. So what do I mean by unconstrained versus constrained? Basically, you have on the left 2 representations of the FPGA resource that can be used. So consider that each small spot of a gray color is a physical circuit that is used in our practical implementation of the recurring function that can be used, sorry. And the blue one are the ones that are effectively used. And on your left, you have what physical resources are used in the unconstrained synthesis. And on your right, you have the ones that are used for the constraint synthesis. So constraint synthesis means that we force the synthesizer to use only physical resources that are located in a specific area. And in red is depicted the routing of the same signal for both synthesis style. The first stuff that we have to do, in fact, in order to assess the validity of assumption, is to build a linear model, so the linear model that I've been speaking about. And for that, we, in fact, built a noiseless linear regression model of degree 1. How we did that, basically consider that we use averaging in order to remove the noise. So that means that for a single input vector, we are measuring the value, and we are repeating the same input vector several times in order to acquire several, and in that case, any trace for this specific vector. And then we average all the traces that we are collecting in order to build a noiseless leakage value. And by doing that for several different input vector, we are collecting different average trace, and based on that and on the value that we know for the fresh key internal value, we can build, in fact, we can compute the coefficient alpha I in order to build our linear model. And we will use the results that can be obtained for the correlation-based side channel security, which is that for using correlation, you're using a correlation attack. Basically, the amount of trace that you require in order to be able to mount this attack is equal approximately to a constant divided by the correlation between the model that you are building and the physical leakage value. And based on that, we perform some correlation computation with different level of averaging for our 3 different synthesis style. And it turns out that, in fact, you can see directly on these 3 graphs. So each graph is for a single congestion level. You can see that considering the linear regression model, we reach high correlation, while when we considered only Hamming weight, we have way lower correlation. So even if we are not saying that we have only first order leakage, because we have not not first order but first degree leakage, since we have not a perfect correlation of 1. We, in fact, conclude from these results that first degree linear regression model captures most of the information. And the second hypothesis that we had to assess was the bounded value of S. So for that, based on this linear regression model, we tried to, in fact, see the loss of information considering a discretized model. So the model using the S pseudolinear bounded function. And for that, we, in fact, discretize our real coefficient using this process. And we also use the correlation chain rule in order to, in fact, see the loss of correlation that we have between our discretized model and the model that was considering coefficient over R. And it turns out that the coefficient between the practical leakage that we were collecting and the discretized version can be expressed as 1 minus phi times the correlation that we had just before. And it turns out that from our practical measurements, using a S value that is equal to 2 to the power 8, we already have a phi value that is below 10 to the power minus 6. Just to be a bit more to provide a bit more of visualization. On your left, you have the coefficient of the discretized version of the model and the real one, considering S is equal to 2 to the power 4. And on your right, you have the exact same plot, but considering S to the power equal to the power 8. And you can see visually that basically on your left, you have still some error in terms of the distance between the coefficients, while on your right, you have something that is pretty the same. So putting things together, from our experimental conclusion, it seems like the assumption that we have made in order to consider, in fact, this S-bounded pseudolinear leakage function are sound. And so the analysis that are made based on these ones, or on this class of function, is sound too. And in fact, for the practical implementation that we have analyzed, we have that considering a fresh key of size 124 bits for the parallel implementation that we are using, and using S equal to the power 12, we have a complexity of attack that is above 2 to the power 124. Going further, we have also analyzed the security when we consider also quadratic terms instead of only linear ones, but I invite you to go and check the paper for more details. So as a conclusion, the LWPR hacking function seems to be also secure when we consider not only Hamming weight leakage function, but a more general one, which is the linear regression model. And it is secure from our analysis if it's implemented using parallelism, which is in fact required. And the more parallelism you have, the better it is for the security point of view. And when the adversary only follows the natural path, attack path that I have described, so trying to solve the algebraic system. As open problem, there are some stuff that we may want to work on in the following month. For example, we would like to maybe base our formal analysis on the cardinality of the leakage function, because that would make feasible to link, in fact, the S bond directly to the measurement apparatus that we are using. We also may want to analyze multivariate leakage function, because we have only considered single variable leakage function for the moment. And we may want to try to have improved cryptanalysis results in order to break the LWPR computation. And in fact, it's basically trying to have adversary that may find another attack path than the one that we have analyzed. And also, why not trying to integrate the LWPR product hacking function or some stuff that are similar in post-country crypto, which was, I think, already done in the Polka paper of PKC this year. At least they try to analyze a bit how it's, for at least the similarity between some operation and the LWPR product. So yeah, basically that concludes my talk.
Thank you very much for the presentation. Since we are a bit tight on time, so I suggest that if you do have questions, please ask him directly during the break. And let's move on to the next one. Do we have the speaker here? You have. So the next one will be about unifying freedom and separation for type probing secure composition. And the speaker is Abdul. Please.
Hello, everyone. Thank you for the introduction. So I'm Abdel, and I'm going to present to you our work on unifying freedom and separation for tight probing secure composition. So I guess by now you all know what side-channel attacks are. They exploit the physical emanation of a device on which a cryptographic algorithm is implemented in order to breach the security, as opposed to the black box model where we actually consider the mathematical robustness of a cryptographic algorithm. And so many countermeasures have been proposed to protect against these attacks. One of the most popular ones is the masking countermeasure, where we aim to split a sensitive variable into n different variables that we call shares in order to manipulate them instead of manipulating the secret variable. So we can do this, for example, by generating n-1 random variables uniformly at random and making sure that the last one would be the combination of the secret with the random variables. In this way, we have that any set of n-1 variables of the n shares are actually independent from the secret. Now, in this case, instead of manipulating the secret variable, we will manipulate the shares. And so an attacker would need more observations, side channel observations, in order to retrieve the secret value. And so as the number of observations grows, and since each observation, side channel observation comes with noise, then we assume that it becomes more difficult for an attacker to retrieve the secret. So as I said, before we manipulate the secret variables, now we want to manipulate the shared variables, the n shares of each secret variable. So we will replace our atomic gates by what we call gadgets that perform the same operation as the original gate, but on the shared variables. So for example, in the first case where we had the addition gate, we will have the addition gadget, which takes as input 2 input sharings and produces the resulting output sharing, which corresponds to the result of the addition. We have the same thing for the multiplication. And so we use another type of gadget, which we call the refresh gadget, which produces an output sharing of the same secret variable, but which is independent of the input sharing. So we need this in many cases for security reasons and for composition reasons that I will show later in the talk. Intuitively, such a gadget would be considered secure if an attacker needs at least n observations to retrieve the secret. So indeed, since we have n shares, we want to achieve the maximal security possible. And so with n shares, an attacker can just simply probe or like observe the value of the n shares in order to retrieve the secret. And we want that with less than n observations, no information can be deduced about the secret. So to reason about the security of masked implementations, the community introduced what we call leakage models. One of the most popular ones is the probing model, where we consider that a circuit is T probing secure for T which is less than the number of shares if any set of T intermediate variables on the gadget or the circuit is independent of the secret variables. Now on the right, you have two examples of addition gadgets. The first one is a bad example because by observing the value of the output share C1, the attacker can retrieve the value of the secret A. The second example is a good one because no single observation can retrieve the value of the secret A or the secret B. Now here we consider probing security for 2 shares, which is why we consider just a single observation for T equal to 1 and N equal to 2 shares. Now, constructing secure gadgets is one thing, but what about composing them? Imagine that we have a circuit composed of just gates, and we want to replace the secret variables by n shared variables, and then we want to replace each gate by the corresponding gadget. How can we compose them in a way that is still probing secure globally? So for this, the community also introduced what we call composition notions that ensure global probing security. One of the most popular ones is the non-interference notion, which says that the distribution of any set of at most T variables must be simulated using at most T input shares of each input. Now on the example that you see here, we give the example of 2 probes on the output of the gadget G4. And this translates to the knowledge of 2 input shares of the gadget G4 if the gadget is 2Ni. Now, these 2 input shares will be the 2 output shares of the gadget G3, and then we will come back to the inputs of G3, and then we go back to the input of G1 and G2 until the probes on the output of G4 translate to the knowledge of at most 2 input shares of each input of the global circuit. So this means that knowing these input shares, a simulator, which is an algorithm that just simulates the distribution, if he knows the values of these input shares, he will be able to simulate the distribution of all the internal probes, which gives global 2 probing security for this circuit. Now we have a stronger composition notion that we call strong non-interference, which just simply splits the observations that we have on the output and the observations that we have on the internal variables. So on this example, if we have all of the gadgets that are 2 SNI, this means from the definition, we have T1 intermediate variables and T2 output variables that are probed. All of them must be simulated using at most T1 input shares of each input. So in this case, if we still have 2 probes on the output shares of G4, nothing propagates to the inputs of the other gadgets, thanks to the definition of SNI. Another example where we have 1 probe on the output of G3 and 1 probe inside the gadget G2, all of them will just translate to the knowledge of 1 input share of the second input, which is the input of G2. So we just have this separation, a stronger notion to separate the probes on the output and the probes on the internal variables of a gadget. Now we also have stronger composition in a stronger model that we call the region probing model, which is just an extension of the probing model. This means that we have a circuit, we will split it in different regions. We can define what the regions are, and each region must be T probing secure. If this is true, then we say that our circuit is T region probing secure. Now, the benefit of this model is that it reduces better to more realistic leakage models, such as, for example, the noisy leakage model that was introduced earlier in the talks. Now, the motivation of our work was a work that was done in 2018, which is called tight private circuits. Now, the authors in this work try to do secure composition in the probing model by carefully inserting refreshed gadgets at specific locations in a circuit in order to ensure global probing security. Now, the composition is tight because they don't insert more refreshed than needed. And the authors rely on the usage of SNI, multiplication, and refresh gadgets, specifically the ISW scheme. While going in the details of this paper, we actually observed that SNI is not a sufficient property for their framework to hold. And so it actually breaks the correctness of their strategy. So I will give more details on this later, but this is where our work started. In terms of contributions, I have to present 2 essential properties from the state of the art. The first one is free SNI. I will give a definition later, which was introduced in the context of secure wire shuffling in the probing model. The other one is called input-output separation, introduced in the context of composition in the region probing model. What we do in our work is that we actually unify and extend both properties, propose efficient automatic verification for both properties and include them in the iron mask verification tool. And we propose gadgets that satisfy both notions. We actually prove that existing gadgets from the state of the art satisfy these notions and use them to correct the flaw in the tight private circuits proof and generalize it, and also then use it to provide more efficient composition in the region probing model. So let me give you the definition of these 2 properties in order to be able to continue the presentation. Here we have an example of a gadget with 1 input and 1 output with 3 shares. So n is equal to 3 shares. And we consider a set of probes on the gadget W of at most 2 probes. If this gadget is free to SNI, this means that for a given set of probes as on the screen, there exists a set of input shares of at most 2 input shares. Now here I give you an example of just the second input, which can be used by the simulator. So if the simulator knows the second input share of the input sharing, then he can use it to perfectly simulate the distribution of the probes in W and the output shares, so the distribution of the values of the output shares of the same indices of the set that he chose. So this means using as a set I, we can simulate W and J, which is equal to I. And we also have a stronger property that says for free to SNI that the output shares, the remaining output shares, still preserve the uniformity and independence property. This means that the probes give information on a subset of the output shares, and the remaining ones still remain independent and uniform. Now, the iOS property, if this gadget is to iOS, then this means that there exists a set I of input shares, but also a set J of output shares of size at bounded by the size of W always, that can both be used by the simulator to perfectly simulate the distribution of the probes in W, which is it's slightly different than the definition of free SNI, which imposes the choice of the set of output shares. Now, one thing to observe here is that the uniformity of the output sharing is implied by the property free SNI, because if you consider the empty set of probes, this means that the simulator must be able to simulate the empty set of probes, which is nothing. And we also have to ensure that any strict subset of the output shares is independent and uniform. So we have the implication of the uniformity of the output sharing. Whereas for iOS, the uniformity of the output sharing is required for the property. So it's an assumption before even considering the property. Which also means, so we also have that for free SNI, the input sharing is fixed for the simulation. So we fix the input sharing, the simulator gets the values of the shares in the set I, and then he does the simulation. For iOS, we fix the input and we fix the output sharings, and then we give the corresponding values of the sets for the simulator to provide the simulation of the probes. The first thing we do in our work is that we generalize both properties to two input gadgets, because then we use them for multiplication gadgets and other gadgets. Now here is just, I summarize what I already said in the previous slide, the definition of free SNI in iOS. The main difference, as I said, is that the set of output shares is chosen by the simulator for the iOS property, whereas it's imposed for the free SNI property. And for the free SNI, we have a condition on the uniformity of the output sharing. Now we can actually prove an equivalence between both properties by relaxing some requirements. The first thing we can do is that we can balance the iOS property by saying that the simulator can only choose the set of input shares, and then the set of output shares would be equal to this set of input shares. Now here we can see that both definitions become similar in terms of the choices of sets, and it remains to show that we still have the output shares, the remaining output shares, that are still independent and uniform. Now, interestingly, this is true. We are able to prove it, and I encourage you to go read the proof in our paper if you would like more details on the proof. On another hand, we can unbalance the free SNI property by saying that, okay, the simulator can now choose the set of input shares and choose the set of output shares, and then move on with the rest of the definition as it is. And in this case, we can prove the equivalence between iOS and unbalanced free SNI. So we have two equivalences between the properties by balancing and unbalancing the choices of the sets. Here I show you a figure that's in our paper, which summarizes the different relations between the notions and also gives the relations with other popular notions, composition notions in the state of the art, SNI, NI, and PINI. So we see that we have an equivalence between the free SNI and balanced iOS and unbalanced free SNI and iOS. Whereas for other properties, we have implications in one way, but not necessarily in the other way. And we provide like a full overview of the different implications and counterexamples in case this is not true. So now that I've given you the definition, let's move to the formal verification of the property. So as I said, what we do is that we include the verification of the properties in the verification tool IROMask. So what does IROMask do? It's made for verification of probing and random probing like properties, and it's based on an algebraic characterization of the expressions of the different probes. So essentially, given a set of probes, it's given as input to IROMask, and IROMask then performs Gaussian elimination on the expressions of these probes, and specifically on the randoms contained in the expressions of these probes, and then use them to mask some of the expressions in the probes. Masking an expression by random value means that no input shares is needed for the simulation. So we can just simulate it as a uniform random value since it's masked. So the probes masked by random value need no input share for the simulation, whereas the remaining one after Gaussian elimination will determine the input shares necessary for the simulator to produce a perfect simulation of this set of probes. Now, to extend this to the verification of free SNI and iOS, we need to recall that given a set of probes, we still need to determine the set of input shares necessary for a simulation, but we also need to verify the uniformity and independence for subsets of output shares, which is not necessarily trivial to do using Gaussian elimination. So how do we do it? Well, in our work, we prove that it is sufficient to do one Gaussian elimination, carefully chosen, in order to find the set of input shares necessary for the simulation, and at the same time, ensure the independence of the subsets of the output shares. Now, this is just to tell you that we have a verification technique that is not worse in terms of complexity than the verification technique for example, SNI or NI properties, whereas we think that these properties are much stronger, much more complicated, but actually in terms of verification, we have something that's almost equivalent in terms of complexity. Next, we show some constructions from the state of the art that satisfy these properties. So typically we have the ISW construction, which was already presented, but I will give you a quick overview to recall how it works. So here we have the 3-share example. Basically, you can see it as as manipulating the shares of the input in a matrix form. So we do the cross products between the input shares. Here we have A1, A2, A3, and B1, B2, B3. We multiply them crosswise. We put them in a nice matrix. Then we mask the upper triangular part by some random values, independent and uniform. And then we do some kind of folding of the lower triangular part and add it to the upper triangular part of the matrix. So we have something that looks like this. And finally, we rearrange them in order to split them into 3 different output shares. So basically, we take the one on the diagonals, we keep them on the same line, and then we move them in order to ensure the correctness of the output sharing. So we add the random value twice on 2 different output shares. And in this way, we have that the sum of all of the output shares gives the result of what we want. So here, of course, I consider F2. That's why I only have additions, but it can be generalized to other fields. We can have additions, subtractions, etc. Now, this ISW gadget has a randomness and gates complexity in big O of n squared. And it is actually known that, or proven in the literature, that this gadget is actually n-1 SNI. So it satisfies the SNI composition notion. What we do in our work is that we prove that it is free n-2 SNI, not free n-1 SNI, and that the refresh gadget derived by this scheme by simply fixing the second output sharing to 1, this way we have a refresh gadget using the ISW scheme, is free n-1 SNI. So we have a trick in our paper that makes us transform the ISW multiplication into something free n-1 SNI, but I don't necessarily go into the details here because it is sufficient for the rest of the presentation to have something free n-2 SNI. Another well-known gadget from the state of the art is the big O n log n refresh gadget, which is more efficient than the ISW refresh gadget. And basically what this gadget does is that it takes as input the n-share input, applies a layer of randomness using n/2 random values, and then does 2 recursive calls on each half of the input sharing, applies another layer of randomness using n/2 random values before outputting the output share. The benefit of this gadget is that it has a randomness complexity in big O of n log n. And so this gadget is known to be, or proven to be, n-1 SNI in the literature. And what we do is that we prove that it is also free n-1 SNI, and we also validate it using IROMAX. So we run the verification tool on the 3-share, 4-share, 5-share version of this gadget and prove that, see that it is free n-1 SNI. So why am I showing you these 2 gadgets? Because I will use them later for the correctness, to use them in the composition notions in the rest of the presentation. So let's get back to tight private circuits. Recall that it does a secure tight composition in the probing model by inserting refresh gadgets carefully at some locations in the circuit to ensure global probing security. And the authors use n-1 SNI multiplication and refresh gadgets. Why is it not sufficient to use SNI gadgets? It's because the authors use and prove the fact that for an SNI multiplication or refresh gadget, n-1 SNI, any set of n-1 output shares is uniform and independent. What we observe and what we show is that this is not necessarily true when we have probes inside of the gadget. So if you don't have any probes, it's fine. But if we have probes, it's not necessarily true. And this is what breaks the correctness of the strategy. So let me give you an example on the ISW scheme with 4 sharing, with n equal to 4 shares. If we have the probes with orange rectangles, and we consider the output share C3, it's not independent and uniform anymore from the probes. So we can't use the SNI property. So what we use instead is free n-2 SNI multiplication and refresh gadgets and prove that the result in TPC, tight private circuit, is still correct, but because they use the ISW scheme, which is actually free n-2 SNI. So it doesn't break the correctness of what they do, but it breaks the generalization of what they do. So we can't use other gadgets beside ISW if we use the results of TPC. The benefit of what we do is that we generalize it and we can use other gadgets that are maybe more efficient than the ISW scheme, such as the big O of n log n refresh gadget. Finally, we do the same thing for the composition in the region probing model. So the framework introduced in 2021 using the IOS property introduces or inserts IOS refresh gadgets between probing secure regions in order to ensure global region probing security. What we do is that we adapt the generalization of the TPC proof to region probing security, which allows us to use any IOS gadgets, not only the refresh gadgets, reducing the number of IOS refresh gadgets to insert, and also increasing efficiency because we can use efficient gadgets such as the big O of n log n refresh gadget or other more efficient multiplication gadgets. To conclude, in this work, we provide an equivalence between the free SNI and IOS property, which came from 2 different worlds, which is very interesting because we are able to unify them and use them to another purpose. And we prove that both of them can be efficiently verified using an already existing verification tool, but by doing some tweaking to the technique. And we prove that well-known gadgets from the literature also verify these notions without doing any more work. And finally, both of these notions lead to more efficient and correct composition, both in the probing and region probing models. Now, I'll show you once again the figure that shows the different equivalences between the notions, and I encourage you to go read our paper if you would like more details on the counterexamples or the proofs that lead to the implication. Thank you for your attention, and I would be happy to answer your questions.
Thank you very much for your presentation. Are there any questions?
I have 2 questions maybe. And now during the talk, I was wondering, is TSNI as a free TSNI implying T-Pini or Pini?
It's not the same thing, no. I don't think they are very comparable because so in the PINI, you don't necessarily have this condition on the uniformity of the output sharing.
I mean, is it stronger?
It's stronger, yeah. Yeah,
So,
it's
but
stronger.
it does imply T-Pini, so you could have another arrow in your...
Well, if we go back to the figures, so yeah, you have free SNI that will imply TSNI, and then you have TSNI that will imply TPINI for 1 input, but then for 2 input, it's a little...
But for 2 inputs, free SNI implies T-Pini or not?
I'm not sure.
You're not sure?
I'm not sure about it, because the PINI is not very well defined for 2 input gadgets. Originally, it was introduced for refresh gadgets, and for 2 inputs, it's a little more... It depends on the viewpoint of how you see the property, but...
I think they did make it also for multiplications.
Sorry?
There are also Pini gadgets for multiplication which have 2 inputs.
Yeah, so yeah.
So it should be defined.
Maybe, yeah. Maybe I should look into it. I can look into it later and tell you what I think.
Okay, thanks. The second question is, okay, that's not what you would like to do, but if you don't need region probing models, so the way you're using your refresh gadget is to cut the big circuit in pieces, which are then a kind of independent.
Yeah.
Could you use in this different regions the same random, also reuse random, if you are only interested in probing security?
Use the same randoms in different regions. So in order to like reduce the number of randoms necessary, I don't think so.
So even if they're separated by this nice refresh.
Well, they're separated, but yeah, I don't know. I'm not sure. Like, I would like to say no, but I don't have any proof right away to tell you that it's not true. But I would be surprised if we can actually use the same randomness in different regions. But it would be interesting to look into the question.
Thanks.
You're welcome. Thank you.
Let's thank the speaker again. That's conclude this session. We do have a break at this moment, and the next session will start at 4:15.